Another important skill to have is solving exponential equations. So solving where x is in an exponent, just like with the graphs, x was in the exponent. This is one of my favorite types of equations to solve. I just think they're fun. So looking at our first example up here, you've got this 5 to the x equaling 5 to the third. And hopefully our brains just tell us that automatically we know x has to equal 3. So asking ourselves, why do we know that that has to be true? Well, it's kind of like a duh, that 5 to the third equals 5 to the third. But the reason that that works is that if our bases are the same, then exponents are equal. Which makes sense. If I was raising 5 to a power and equaling it to 5 to a power, well, those powers have to be the same if they're equal to each other. So if I have a situation where my bases are already the same, I should be able to set those exponents equal to each other. Maybe it's more complicated than this, 2x plus 1 equal to 3. But I'm setting those powers equal to each other to say, I know they have to be the same. So for example 1, we don't always have this situation where I have my bases the same to start with. Sometimes I have to get the bases the same on my own. The way that we're going to do that is by rewriting our base as something equivalent, that is that base raised to a power. So for example, in this first example, I have 5 being raised to a power and then 25 being raised to a power. If I could rewrite 25 as 5 to a power, then they would both have the same base. So sometimes you're going to be rewriting one of them as the other base to a power. Sometimes you'll have to rewrite both. But in this case, hopefully we can see I can rewrite 25 as 5 to the second. It's still raised to the fourth, so you've got 5 to the second to the fourth. And now I can say, anytime I'm raising a power to a power, I'm multiplying those. So if you're multiplying like x to the second times x to the third, you add them. But if you've got x to the second to the fourth, you're multiplying. So 5 to the 8th. And now I can use that logic that we used at the very beginning, that if the bases are the same, the exponents have to be equal to each other. So this isn't necessarily that this is equivalent to 2x equals 8, but it follows from that. So if this is true, then 2x has to equal 8, so x has to equal 4. Very easy to check these with a calculator. Try, 5 to the 8th and 25 to the 4th, and you should get the same thing, which makes some sense here because that would be 5 being multiplied by itself 8 times. 25 to the 4th is also 5 multiplied by itself 8 times. So sometimes you get something a little bit trickier where in this case I would always try raising or changing the larger base as the smaller base to a power. So you might start by saying, okay, can I rewrite 16 as 8 to a power? And we can't. We might be tempted to say 8 squared because 8 times 2 is 16, but you're talking powers here, so 8 to the second is 64, way too big. So that means I'm looking at changing both of these as some base to a power. So if I tried like 4, I've got 4 squared is 16, but I don't have a way of writing 4 to a power to get 8. And then you're like, okay, I need to go smaller. Well, 2 to the third is 8. Still have the exponent that was there. And then 16 is 2 to the fourth. So sometimes we'll rewrite both. If you have a situation like this, remember power to a power, we're multiplying. And in this case, we would need to distribute the 3 to both the x and to the 14. Let's see, we got a 2, 42. And same thing here, 4x. And then I could take that step in logic that if my bases are the same, the exponents have to be equal to each other. Again, add 3x to both sides. Okay, last example. Sometimes we see a fraction involved, so they're not both whole numbers raised to a power. And my suggestion for a fraction is to change it at the very beginning. So as soon as we see there's a fraction involved, instead of having 1 over 9, I'm going to rewrite this as 9 to a negative first power. Remember, if I have an exponent, I can always move it from denominator to numerator or vice versa and change it to a negative exponent. A lot of times it's more helpful to change it from negative to positive, but in this case it is helpful to change it from positive to negative. And now this is going to operate the same way as any of the other ones. I'm looking for either changing 27 to 9 to a power. That's not going to work, so I need to rewrite them both as the same base to a power. Hopefully you thought of it. We've got a 3 squared and a 3 to the third. So my exponents will end up being a -2 and a 3x. So I get a -2/3. So for some of these, I think you can work in your head a little bit. Sometimes students can use some more like trial and error, or okay, I could see that this was going to be equal. Whenever it comes to the fractions, it's quite a bit more difficult, I think, to guess what that's going to happen. Remember that 2/3, whenever I raise something to a fraction, that the numerator is a power and the denominator is a root. So just reminding ourselves that if I'm raising 27 to the -2/3 power, that means I've got this 27 to the -2nd and then taking the cube root. Actually, I'm going to put the cube root on the inside. I'll put the 27 out here. And then if I have a negative power, that means it's in the denominator. So I've got a cube root of 27 squared. And if we simplified this, my cube root of 27 is 3. 3 squared is 9. So that's why that -2/3 power makes it equal 1. The last thing that we're going to look at, and this is a little wordier, if you're not operating from printed notes, then you might hold off on writing this all down and see if it's making sense to you. I think, and maybe you want to write down just what things stand for, but see what makes sense and what you need to add to your notes before you write all of this down. And the last thing we're looking at is compound interest. So looking at either compounding something per year, which just means that they're going to tack on that interest once, or sorry, if it's one compounding per year, then it would be once per year. If it's quarterly, then that's 4 times per year. If it's monthly, 12 times per year, however many times per year that's happening. Or for continuous compounding, it literally is compounding constantly, continuously. That rate is always being added to what is currently there. And this could be a bank account, it could be a home loan, something like that, anything that has interest attached to it. So the biggest part, you do not have to memorize these formulas. I will have them for you on the test, on quizzes, whatever we do with it. But we do need to understand how to use them. So first, in both of these equations, it starts with a P, and that P stands for principal, which is kind of fancy for initial amount. So this could be an initial amount that grows, it could be an initial amount that decays. If you're talking about the price of a car, how much it's worth, then it's going to depreciate over time. If it is the amount of money in your bank account and you're earning interest, then it's growing over time. But this is what you start with. In this first formula is talking about the number of times per year that it's compounded. So number of times compounded per year. You've got R in both of your equations is the interest rate. In order to put this into a formula, I do have to look at the percent as a decimal. So if you're dealing with like 12%, that is 12 out of 100. which is 0.12. So before I put it into my formula, if we're talking 12%, I'm just moving that decimal 2 places, and that's what I'll put in for R. And then the last thing is T, which is the amount of time that has passed in years. So if we want to know how much that car is worth after 6 years, then T is 6. So just a few examples here. The first one, we've got a total of $12,000 being invested at an annual interest rate of 9%. We're finding the balance after 5 years if it's compounded quarterly. So a lot of variables. We also need to decide which formula we're using. So a little hint here, if they're wanting to compound continuously, they will use the word continuous. So it's kind of obvious for these. Also, if it's talking about the first formula, it will tell you it's compounded quarterly, yearly, monthly, something like that to let you know how often it is compounded. So we're using the first formula, starting with P. Our principal or initial amount will be this $12,000 that we're investing. We've got our interest rate as 9%, and remember, before we plug it in, we're moving it to the decimal 2 places, so we're plugging in 0.09. We've got the amount of time that has passed, so our T is 5, and remember, it's always years. And then our last number, we're still missing the N. Remember, the N is the amount of times that is compounded per year. So if it's compounded quarterly, that is 4 times per year, so our N is 4. So whenever we go to plug in all of those values, we've got our principal, 1 plus our rate, 0.09, over the amount of times compounded, and our 4 times the amount of time. Notice that this exponent is the amount of times that it's compounded, because if it's compounded 4 times per year for 5 years, it ends up being compounded 20 times. So that will end up being the amount of times that you are compounding it. So then from here, we will definitely use a calculator. I would just be careful, simplify maybe what's in parentheses first. Go ahead and put this as 20 instead of 4 times 5. Be careful there. Definitely try this and make sure that you are getting what I'm getting. But you should get about 18,726 and 11 cents. Whoa. Somewhere around there. 9% is a great interest rate. They gained about $6,000 there. Some of these questions are very realistic and some of them not so much, but if I can find an interest rate of 9%, sign me up. Last one, you've got finding the balance if that same amount is compounded over those 5 years continuously. So we've got less information for the second formula. We still have this same principle that we're starting with. We'll have that E, remember we talked about earlier, is like 2.7. It's a number, we are raising it to that same, your rate this time, so 0.09 times the amount of time that has passed, your 5 years. And whenever we put that in the calculator, you should have 18,819.75. So quarterly versus continuously, at least for this amount of money, wasn't a huge difference, about $100. It is a difference. It's always going to be more if we're compounding it all the time versus every once in a while, but it is a little bit more here. If you are not getting these when you're putting them in a calculator, I would try it a couple of times, but then if you're still not getting it, come into the meet, ask me those questions so that we remedy however you're putting it into the calculator.